The first talk is by Isabella Mastroeni on abstract local completeness.
Okay, thank you. So, welcome to everybody. In this work, I will show how we exploit a strong connection existing between two notions for modeling properties of programming languages. This connection is really strong and provides different points of view, different perspectives on the same aspects. So, local completeness is the standard way used in abstract interpretation for modeling precision of abstract domains, while abstract non-interference is a notion of a hyperproperty, is a notion that was introduced for language-based security, but then generalized, and that provides a deep insight in the way of properties of the input may affect properties of the output. So there is a strong connection between these two notions, and we exploit them to provide a new insight in the notion of completeness, a new way of looking at completeness. So let's start from the introduction of completeness. Very high-level introduction. I mean, in abstract interpretation, usually we have soundness. So we have the semantics of a program, in particular, and that may fail to be decidable, to be computable. But we want anyway to provide an answer to whether these semantics satisfies or not the specification. So since the program, the concrete semantics is undecidable, we usually try to prove whether a property of the semantics satisfies the specifications. So we clearly, when we write something like this, we have anyway an abstraction of the concrete semantics. So still we have the decidability problems. And this means that we need to compute an abstract semantics which soundly approximate the abstract property. And in this case, if the abstract semantics satisfies the specifications, that by inclusion we have also that the concrete semantics satisfy the specification. Anyway, as already just observed, we may have false alarms because the abstract computation may introduce some noise, and this noise may lead to fail the inclusion relation of the abstract computation in the specification, and this means that we cannot say anything about the concrete semantics because we lose the inclusion relation. So what we can do is just to try to keep this abstract computation as closer as possible to the real abstraction of the concrete semantics. And indeed, when we have completeness, it means that the abstract computation precisely compute the abstract property of the concrete semantics. And in this way, if we are able to prove that the abstract computation satisfies the specification, then we can more easily, with more precision, provide the answer for the concrete semantics. And this is completeness. Anyway, clearly we have however, we add anyway some noise, which is the fact that we consider a property of the concrete semantics, and there are other approaches like adequacy for trying to control in this kind of loss of information. But when we have completeness, we clearly keep this loss of information as small as possible. So this is completeness, and it is usually described as a property of the abstract domain on the concrete semantics, and it is usually introduced as a universal quantified property. So we have completeness if for any possible input we have this equality that holds. And this is the problem because completeness as a static analysis is an intentional property, so it strongly depends on how the program is written. And since it is also universal quantified, it is a really strong property and very hard to be satisfied by a generic program. So recently it has been weakened with local abstract completeness, and which requires the completeness only on a specific input or set of inputs, with making really a local and focused property. So the relation with abstract interference, so this way that we are going to, that I'm going to show, look at completeness as an hyperproperty, allows us to find an intermediate weakening of completeness that makes it maybe more useful for characterizing precision. So let's see what is absolute non-interference. As I said, it is a notion introduced in language-based security, but then generalized in, as a generic property on programs. And it is an hyperproperty because it doesn't hold on single computations, but it holds on sets of computations. In particular, it is a two-hyperproperty because it compares pairs of computations. And usually it requires that for any possible x, so here we have 3, for example, we take the set of all the elements with the same abstraction, so the abstraction of x for all the possible inputs. We consider the computation of the semantics on these inputs, and we consider the property of the output of these semantics. So what is the requirement? This is the context. These are the ingredients that we consider for absolute interference. The requirement is that for any possible y, value y, input y, sharing the same property of x, for each x, the computation of the concrete semantics must have the same abstract property as the abstraction of x. So values with the same abstraction in input must have the same abstraction in the output. And this has to hold for all the possible inputs x's of the program. So we have a double universal quantifier, but it's double because we have to compare pairs of computation. So this corresponds precisely to completeness. It has been shown, formally proved, that requiring that for all x, requiring this kind of condition corresponds precisely to have completeness for all the possible inputs of the program. Since it is a universal quantified property, then if we have at least one x for which there exists at least one value y that has a different output property, then absolute interference and also completeness doesn't hold. So this is a notion introduced in the language-based security and now compared, proved to be equivalent to completeness. And now, since there exists this local completeness introduced in the literature, we wonder what it means for the absolute interference perspective to be local as completeness. So let's focus on a single x, clearly, first of all. This was the original requirement. And at this point, we observe that to require local completeness means surely to avoid the universal quantifier on x, as for local completeness, but also it means to weaken the output relation for the values y sharing the same property of x. So when we make local completeness, we are weakening the notion of completeness not only from the point of view of the quantifier, because we fix only one x, but also from the point of view of what we require as a property, as condition. So it is really a weak property. And also this observation suggests us that maybe there is an intermediate weakening of completeness, because we can still avoid the universal quantifier on x, but we can keep the same requirement as before in the output. So we decided just to investigate what is the meaning of just requiring the relation of absolute interference only on a fixed x, allowing anyway y to move to be universal quantified, clearly only in the set of all the elements with the same abstraction. And requiring that the output must be the same, must share the same property as before. This is a new notion, and indeed it doesn't correspond neither to absolute interference because we change the quantification, but also it doesn't correspond to local completeness as it was introduced in the literature. And we call it a local abstract completeness because in this case we still are localizing the observation, but not on a concrete value, but on an abstract value because we fix alpha of x mainly. And this is still the same property as before, but only for one x. And if we compare it with local completeness, it means that we are requiring local completeness on a set of inputs, which are all the inputs which share the same abstraction as x. So the idea is that we have local standard completeness, which is a universal quantification on x, and we have local completeness, we just fix one x, And we have absolute local completeness, which fixes X, fixes the property of X, and requires that completeness holds for all the elements inside this set. And the interesting aspect is that by changing the abstraction, we change the property. Because if we take as abstraction the top abstraction, we get back the global completeness. While if we take as abstraction the identity, we get back the local completeness. But in the middle, we can just tune the way we are looking, the dimension of the sets we want to consider for checking completeness by using this abstraction. So let's see on an example, very easy, very simple example. We consider the standard sign domain, the most representative sign domain. So we have greater than 0, different from 0, equal, lesser than or equal, and greater than or equal. And we have the function making the square of the successor of X. And we wonder whether this domain is complete, globally complete, for the function f. So we take, for example, the input c, minus 2, 0, 2, and we check what happened for sign f, sign, which is the absolute computation. And we see that, indeed, we obtain as absolute computation the sets of all the greater or equal than 0 numbers. Because clearly the square of the successor takes, if we have minus 1, takes also 0, not only the greater than 0 numbers. So let's see what happened to the abstraction of a concrete computation of the same value. In this case, since we have minus 2, 0, and 2, we only get positive numbers. And then we get only positive numbers as a result. So we have a loss of precision. So we don't have global completeness because we have found an element on which completeness doesn't hold. So let's see another possible input. In this case, we take minus 1, 0, 1. We again consider the absolute computation of f. Clearly, this computation is precisely the same as before because the abstraction of this c is the same as minus 2, 0, 1, the same signs. But then we compute the abstraction of the concrete computation. And in this case, we have minus 1 that introduces 0. So the abstraction is precisely the same, all the elements greater or equal than 0. So in this case, local completeness holds. So we wonder whether absolute local completeness holds. And we observe that the two elements we considered, minus 1, 0, 1 and minus 2, 0, 2, have the same sign abstraction. So they are precisely a candidate for checking whether absolute local completeness holds or not. But unfortunately, we have, as we observed before, we have different results for this output observation, I mean the observation of the computation of f, and therefore absolute local completeness, in this case, for this abstraction, doesn't hold on these points. So in this case, we have local completeness, at least on one point, but we don't have absolute local completeness, and clearly also, we don't have global completeness. Let's see another example. We take this input element, 0, 2, and 4, and we first compute the abstract execution, and we get back all the positive numbers because we lose the 0 in the abstraction. And we compute the abstraction of a concrete computation, and again, we lose the 0, and so we get back to the same value. So in this case, we have local completeness on this point. So again, let's try to see if, in this case, we have or not absolute local completeness. And so let's consider all the elements with the same sign abstraction as C, which means that we take all the elements where there is 0, and at least one positive number. For example, 0, 3. And let's check what happened with the absolute computation. The absolute computation provides all positive numbers. And if we compute the abstraction of the concrete computation, then we have, again, the same absolute value. And since it depends only on the fact that we have 0 and all the positive and at least one positive number, which is precisely the fact that they have the same abstraction, clearly it's easy to check that in this case, for these points, we have absolute local completeness. Okay, so this was an example just to show that indeed we are in the middle. We are really in the middle between local completeness and global completeness. And that the fact is that we can tune the set of elements on which we have to check completeness by using this abstraction. So which was this is the definition of the completeness. The first thing that we characterized was to understand when an abstract domain satisfies abstract local completeness. In this case, there is a slight difference as before because we have two different abstractions in input and in output. In general, this is the most general characterization of both of completeness and abstract non-interference. And in this case, it's necessary because you are transforming, if necessary, the output abstraction. So we keep them maybe different. And in this case, what happened? We define this predicate blind, which is defined in terms of what we need. And if all the elements of the output observation satisfy this predicate, then we surely have abstract local completeness. How it is defined is predicate. We consider a concrete element, and therefore the abstraction of it, A, is the abstract element we fix. Then we take all the elements with the same abstraction as abstract local completeness requires. We compute the concrete semantics, it is a definition, and we take this set depicted in green, which is capital gamma of A, which is the set of all the elements that must have the same abstraction to satisfy abstract local completeness. So we say that an element in the output observation D is blind if it is unable to break any of this set. What it means formally? It means that if it is greater than at least one of the elements in this set, then it is greater than the list upper bound, namely greater than all the elements in the same set. In this way, it is unable to break this set and unable to break completeness. So if the output domain, all the elements of the output domain satisfy this property, then with respect to A, then we can say that the abstract local completeness is satisfied for A. And how can we use the same transformation for having the same abstraction in input and output? We just apply a fixed point iteration. And in the worst case, we get the top, clearly. But we reach a fixed point. So this is a way for simplifying domains towards abstract local completeness because if we have an element which does not satisfy this condition, we just keep only the elements, we erase all the element D that cannot satisfy this predicate blind, and we keep only the elements that satisfy this predicate. And they form an abstract domain, so it's, I guess, still an abstraction. So this is a formal representation just to better understand how it works mainly. And, but if we want really to compute, to verify local completeness, then we need some more effective process for checking whether the property is satisfied. In this case, since our approach is language independent, we consider a very simple language, is a regular language, where the expression is the language of the basic statement, so for example, assignment and skip operation and guards. And then we have the sequential composition, we have the branch, and we have the loop iteration. So when we can define the abstract semantics depending on the abstract domain we are considering. And then we can prove a triple where we have 3 elements, which is the first one is the input that we fix. So the input for which we want to check whether the abstract completeness holds or not. Then we have the other element is the program R, and the last element D is just the characterization, as we can see later, of the output observation that we have when we compute the abstract semantics. So when we are able to prove in our proof system a triple like this, then we are implying, is a stronger condition, but we are implying that absolute local completeness hold for all the elements C prime sharing the same absolute property as C. And in particular, we have two conditions that are satisfied. First of all, we have absolute local completeness, which is given by the equality between the first and the third element of this equation, because the first one is the absolute computation of the program on the absolute value of C. And the last one is the absolute value of the concrete semantics of C prime. Should be C prime. It's the same because half of C is equal to half of C prime, so it's not important. But anyway, this is completeness. And we also require that the abstraction of D is precisely this output value. So we have two conditions, and this way it is stronger, what we prove with our proof system. We have completeness, absolute completeness, local completeness, and we have the absolute value of the program, the concrete program on the concrete input. So this is the proof system. We have this very simple set of rules. The first rule transfer allows us to, we have to prove directly local completeness on expressions, which are maybe assignments and guards. And so when we can prove local completeness, we have the triple holding. Then we have the relax property, allowing us to relax the input or the output value in order to can apply the other rules like sequential composition, where as you can see, the output D prime must be the same as the input value for R2. So if they are not the same, we use relax for making them, if possible, making them the same value. And also we have the iteration and the recursive rule for loop iteration. And also in this case, the relax rule is important for the rec rule in order to make D prime and C or D prime corresponding. And then we have a rule for the join operation, so for the branch, and that allows to combine the output values when the inputs are the same. So with these rules, we can prove whether a program soundly satisfies absolute local completeness. So it is clear that this proof system is only sound, it's not complete. So if we can prove that a program with applying this rule satisfies the triple, then we have absolute local completeness. But if we are not able to prove it by using these rules, it doesn't mean that it does not satisfy absolute local completeness, because we are proving something stronger. So just a final example for the application of these rules. We have a very simple program, and we have as input -100, -10, and 0. Clearly, the absolute domain is sign, and we wonder whether this program satisfies absolute local completeness for this input, concrete input. So we can prove that the first guard x less or equal than 0 is local complete for the provided input. And we can also prove that the assignment x takes x multiplied by 2 satisfies local completeness, absolute local completeness for the input, which is the output of the guard. So we can apply the sequential rule, and we obtain that the sequential statement satisfies local completeness. And there is also the star that is missing here anyway. And then we can prove local completeness of the other guard. And in the middle, I forgot to put the rule for the loop iteration, but it holds. And finally, by applying the rules, we can prove that the whole statement satisfies absolute local completeness with respect to this input statement. And we have also that the abstraction of the absolute property of the output is equal 0 in this case, because we have the precise value in the absolute domain. So this is the idea of the application of the rules, just for proving that we can indeed prove some interesting absolute completeness properties. So concluding, we introduced this approach formal approach for characterizing, for weakening, and also tuning completeness, because, as I said before, completeness is a strong, really strong property because it is intentional, it depends on the way the program is written, and it is universally quantified. And this is a problem, so it may be a problem, so we need to weaken this property. Local completeness is an interesting weakening, but it goes directly on the opposite side. It's focused only on single inputs. So this was an intermediate way just to, as I said before, tuning on which set of elements we can prove completeness. Anyway, the fact that it is intentional may be also exploited for other interesting results. So we can try to design program transformations for making program complete or incomplete for a specific abstract value. Some transformation like this exists for global completeness, exists for abstract non-interference. So maybe we are able to characterize them also for abstract local completeness. Why this could be interesting, for example, for incompleteness, because it has been shown that completeness is a way for characterizing, for example, obfuscation, because if a program, we want to obfuscate a program, we just make it incomplete with respect to what we want to hide. But since the completeness is very strong, weakening completeness is really weak. So this is, again, a way of being in the intermediate part. And also we can try to combine with metrics, so obtaining some kind of partial, instead of requiring the equality, we could require just to have a distance between the results and to understand. It has been defined for completeness. We would like to see what happens for abstract local completeness. That's all.
Okay. Thank you. Okay, questions? Kick off the discussion and then let people pick up. So it's really interesting the use you make of regular expressions to do these proofs, and you showed these syntactic rules. Can you put the slide? I actually had two questions, one technical and one just more general. The rules for recursion don't guarantee this is the least fixed point. Is this a problem, or is it's fine? You just want to unfold, basically.
Yeah, exactly.
And the other question I had, I mean, it is known that for regular expressions, a more semantic-driven reasoning can be more efficient in computing not only that the proof is correct, but also that you can find counterexamples more easily. Have you tried anything in that along those lines, using sort of by-simulation-like reasoning, or have you only done the syntactic?
No, we only made the syntactic. We are investigating different way of looking at this. Semantic ways surely can be a very interesting direction, but also incorrectness. I mean, if it is useful for understanding when it doesn't hold. If we can characterize for which abstract points we are complete and for which we are.
Yeah, that was exactly.
It's working in progress. Yeah. I mean, we are thinking of it, we are working on it. And
the last question, I mean, early in your talk you were talking about hyperproperties and how these things are hyperproperties. Did you exploit any connection with actually proof techniques for hyperproperties, or this was sort of just an observation at the beginning?
It's a dream of work. I mean, we realized when we modeled abstract non-interference, we realized that abstract non-interference was an hyperproperty. We investigated from the semantic point of view. And we had several discussions also with Patrick about logics, and he has a popular paper about this, and also with Peter. And is a way, a road that we want to make, and something we want to study, but still we don't follow that direction yet.
Okay, cool. Other questions? Okay, if there are no other questions, let's thank Isabella again and move on to